For decades, the engine of our digital age, the transistor, has been on an incredible shrinking spree. Moore's law saw these microscopic switches, the heart of every computer chip, become tinier and more numerous, fueling an explosion in computing power. At the core of each transistor is a gate, controlling the flow of electrical current, separated from the main channel by an insulating layer called the gate oxide. As engineers pushed for smaller, faster transistors, this insulating barrier had to become unimaginably thin, eventually just a few atoms across. And that's where the bizarre rules of the quantum world began to assert themselves, creating a profound challenge: quantum tunneling. Imagine an electron approaching this ultra-thin insulating wall. Classically, if it doesn't have enough energy, it should bounce off. But quantum mechanics paints a different picture. The electron, behaving like a wave, has a non-zero probability of simply passing through this classically insurmountable barrier. It doesn't break the barrier, it tunnels, as if a ghost phasing through a solid wall. For transistors, this is a critical problem. When the gate oxide becomes too thin, electrons begin to tunnel through it, even when the transistor is supposed to be off. This creates leakage current, meaning the switch no longer reliably stops the flow. It wastes power, generates excess heat, and fundamentally limits how small and efficient we can make these vital components using traditional designs. The probability of tunneling is exponentially sensitive to the barrier's thickness and height. The thinner the barrier, the higher the chance an electron will tunnel. This effect isn't just a nuisance for chip designers. It's a direct manifestation of the wave nature of matter and the Heisenberg uncertainty principle. An electron's position and momentum cannot both be precisely known. This inherent fuzziness allows it to borrow energy for an infinitesimal time to penetrate the barrier. Quantum tunneling isn't always a problem, though. It's a fundamental process responsible for nuclear fusion in stars, radioactive decay, and is even exploited in technologies like scanning tunneling microscopes. But for the relentless miniaturization of classical transistors, it represents a true quantum limit, forcing us to explore entirely new materials and computing paradigms to continue our technological advance. Imagine a voyage to a world forged not of rock or ice, but of gleaming metal, a celestial body unlike any we've ever visited. This is the bold ambition of NASA's Psyche mission, a journey to the unique main belt asteroid known as 16 Psyche. This remarkable object, orbiting the Sun between Mars and Jupiter, is one of the largest metallic M-type asteroids, stretching about 173 miles, 280 kilometers, across at its widest point. Unlike its rocky or icy neighbors, Psyche appears to be incredibly dense and composed primarily of metallic iron and nickel, much like Earth's own core. This has led scientists to a captivating theory. Psyche might be the exposed, stripped-down heart of an ancient protoplanet, a planetary building block from the chaotic early solar system that lost its rocky outer layers through violent collisions. Launched in October 2023, the Psyche spacecraft is propelled by an advanced solar electric propulsion system. While en route, the mission team successfully navigated a minor issue with a fuel line valve by switching to a redundant backup system, ensuring the spacecraft remains on its precisely charted course. Its journey includes a crucial Mars gravity assist in May 2026 to slingshot it towards its distant target. Upon its planned arrival at 16 Psyche in August 2029, the orbiter will spend nearly 2 years using its sophisticated instruments to answer fundamental questions. Is Psyche truly a planetary core, or is it a different kind of unmelted primordial material? What are the ages of its varied surface regions, and what does the landscape of this metal world actually look like? Scientists will also investigate its precise metallic composition, searching for light elements similar to those expected in Earth's core, and try to discern the chemical conditions under which it formed. The Psyche mission is far more than an asteroid visit. It's a deep dive into the very processes that built planets. By studying this unique metallic world, we hope to unlock secrets about how planets differentiate, how cores form, and the fundamental building blocks that created Earth and its rocky siblings, offering a rare glimpse into the hidden hearts of planets.